All right. So, new chapter today. Today I would like to start talking about bonding in coordination compounds. So, in particular, I would like to talk about bonding theories that are able to explain the bonding in coordination compounds. So let's start out from a very general consideration. Let's think about what good theory in general should be able to do, and then what a good bonding theory should be able to do. So when we think in the most general terms, what do you think should a good theory generally be able to do? Also, suggestions from virtual students are welcome. So a good theory generally is able to make a lot of explanations and predictions based on a very few reasonable assumptions. Okay, so the fewer the assumptions and the more explanations and predictions, the better the theory can be considered. So let's apply this principle to bonding theories. So what do you think a good bonding theory should be able to do? So generally, it should, of course, be based on a very few assumptions, but what do you think should it be able to explain and predict? Well, it should certainly be able to predict, for instance, the number of bonds. Okay, it should be able to predict the type of bonds. Okay, and then it should also be predict the shape of the molecule, as well as properties of a molecule. For instance, chemical reactivities, but also, for instance, optical properties. Okay, so these are the general criteria. So we should be able to explain and predict the number of bonds and the shapes of the molecule. Yeah, I forgot the magnetism, because that relates to the number of paired and unpaired electrons, respectively. Then the stability and the reactivity, as well as the optical properties. Okay, so now let's think about what bonding theories do we have available for coordination compounds. And there are actually overall 3 bonding theories that are being used in coordination chemistry. So they all have advantages and disadvantages to them. So the first one is the valence bond theory. Yes?
It's like, is mine a crystal field?
Pardon me?
Is mine a crystal field?
Yeah, another one is the crystal field theory, and the third one is actually the ligand field theory. But let's very briefly talk about valence bond theory. So you know valence bond theory from organic chemistry. So valence bond theory is the theory to explain covalent bonds. And in classical valence bond theory, we assume that we have one electron in a frontier orbital of a partner. And well, when we have 2 partners that react with each other, then that leads to the overlap of the valence orbitals, and then the respective electrons are being shared. And shared electrons always means covalent bond. So in this way, the valence bond theory can explain the covalent bond. So that's the basic principle. So now we can adjust this slightly for the coordination chemistry, because coordination chemistry we think of a bond as a donor-acceptor interaction. So we say, well, we still have our two valence orbitals, but now one is being completely filled, that's the orbital of the donor, and one is completely empty, and that's the orbital of the acceptor. Now we again just overlap these and make a covalent bond. Okay, so the resulting covalent bond is fundamentally not different than the regular covalent bond. It's just it has formed in a different way. But certainly this way one also can also explain the covalent bond. Okay, now the valence bond theory has some use in. So we got it solved. The problem was that the battery was empty. So if that we could just replace the batteries, it just had a couple of batteries. You could just do that and the problem would be fixed.
These were yours or?
These are not my batteries.
Okay.
No. These are university batteries.
Gotcha. Okay. Yeah, I brought batteries just in case.
Okay, thank you. Yeah, so valence bond theory plays a certain role in coordination chemistry, but it has a lot more limitations than it has in, for instance, organic chemistry or main group chemistry in general. So it can explain certain shapes of complexes within certain limitations, and also in some cases the magnetism. But it can inherently not explain optical spectra, just due to its nature, because optical spectra always do the electron transitions. So the second theory is, so Magnus said, the crystal field theory. And the crystal field theory has the advantage that it's pretty simple to use, and it can fairly reliably make predictions about the shapes of the complexes, and it can also make reliable statements about the magnetism of complexes. The disadvantage is that it is actually based on repulsive electrostatic interactions and not attractive interactions. And in this way, it fails actually to explain what holds a molecule together, which forces hold a molecule together, why there are actually bonding forces. Okay, so this is the limitation of crystal field theory. Just to say where the name comes from, it was actually originally developed for ionic crystals to explain the color of ionic crystals, but it has later on been found that it can also explain properties of molecular coordination compounds quite well. So last but not least, we have the ligand field theory. So the ligand field theory is the most powerful theory. It can explain the number of bonds, the shape of molecules, can explain magnetism as well as optical properties, but it's also the most complicated theory to use. So ligand field theory is basically nothing else but molecular orbital theory applied to coordination compounds. So when we discuss this theory, we will review what we have learned about molecular orbital theory, modify that slightly, and then apply it to coordination compounds. So let us start out with the valence bond theory. So let us apply valence bond theory to a number of complexes, and let's see how well it works to explain the number of bonds and the shapes of these complexes. So for instance, we have here an octahedral complex. So this hexaamine chromium 3+, as shown here. So we have here a chromium 3+ ion, which is octahedrally coordinated by 6 amine ligands, and we view the bonds in between the chromium and the nitrogen is dative bonds. So that means that all the electrons in the bond are actually coming from the nitrogen, and we say that the chromium itself doesn't contribute electrons to the bonding, it just provides its empty valence orbitals. Okay, so now in order to develop valence bond theory for this octahedral complex, we would first look at, well, what are the valence orbitals of the chromium? So we know where the chromium is located in the periodic table. So chromium is located in group 6 of the periodic table. So it has 6 valence electrons. The electron configuration of the chromium, we have learned, is a somewhat special case because we can have 6 unpaired electrons when we occupy the 4s orbital only halfways and basically move the second electron, which would normally be in the 4s, into the 3d. Then we can also have 5 unpaired electrons in the 3d subshell. So we have only unpaired electrons, and that represents a particularly stable electron configuration. So now, in addition to the 4s orbitals, we could also assume that we have 4p orbitals available. So now this here represents a neutral chromium, okay? But now we say we have a chromium 3+, so we actually remove 3 electrons. And so therefore the chromium 3+ ion is so-called D3 ion, 3 electrons in the 3d orbitals. So like I mentioned before, we can also consider the 4p orbitals as valence orbitals because we know that they should have a very similar energy to the 4s orbitals. S and p orbitals of the same shall always have very similar energies. Okay, so now we can check if we can actually make six bonds. So these bonds would need to be don't accept the interactions. So that means that we would actually need 6 empty valence orbitals to make 6 bonds. So do we have these 6 empty orbitals available? We see we do have these 6 empty orbitals available. So that's the first one, the second one, the third one, the fourth one, the 5th one, and the 6th one. All right. So now the 6 amine ligands could donate their electrons into these 6 empty valence orbitals. Okay. So certainly we could make 6 bonds, but would we be entirely happy? The answer is not quite, because not only do we need to explain 6 bonds, we also need to explain the shape in the fact that these 6 bonds are all equivalent, yeah, pointing to the vertices of the octahedron. Now you see that the 6 valence orbitals here are certainly not energetically equal, and they would also have different shapes pointing in different directions. And that's unsatisfying when you want to explain 6 equivalent covalent bonds that point to the corners of an octahedron. So what valence bond theory does in this case, and you know this from organic chemistry, it uses the concept of hybridization. So it mixes the valence orbitals mathematically, and what results is hybridized orbitals that are then being able to explain the shape satisfactorily. So now in this case, we have 6 valence orbitals available. So there's 2 d orbitals, the 4s, and the 3 4p orbitals. We can therefore mix these and make 6 dsp3 hybridized orbitals. So these have now the property that they're all equivalent. And when you analyze the shape, you will find that they all point toward the vertices of an octahedral. Okay, and that's exactly what we need in order to explain the octahedral shape. So what we can do now is that we take our chromium with these 6 sp3 hybridized orbitals and take our ligands and orient the electron lone pairs at the ligands appropriately so that they can overlap with the D2 sp3 hybridized orbitals to make the 6 bonds. Okay, and so by approaching the NH3 ligands, basically the donation of the electron lone pairs into the empty D2 sp3 hybridized orbitals takes place, and we can formally fill them with 12 electrons. So now we have satisfactorily explained the 6 bonds. In addition to that, we have explained the shape of the molecule. So can we, for instance, also explain the magnetism? So we can distinguish basically between 2 types of magnetism. Diamagnetism, that is when we do not have any unpaired electrons, and paramagnetism when we have unpaired electrons. We can experimentally distinguish between diamagnetism and paramagnetism by making a so-called susceptibility measurement. So the basic principle is that when you have a diamagnetic compound, it's repelled by an external magnetic field, and when we have a paramagnetic compound, the compound is attracted by an external magnetic field. So now, what type of magnetism would valence bond theory predict here? Diamagnetism or paramagnetism? Yes.
I mean, are we looking at overall or by orbital? For the diagrams and the power axis. This is like, of course, like the whole D2 SP3 orbitals are all like diamagnetic, but then the 3D ones are all paramagnetic. So would that take overall paramagnetic property?
Yeah. I mean, what is the magnetism of the desired complex? The entire thing.
So I would say paramagnetic.
Yeah, that's correct. And the reason is that valence bond theory would predict that we have 3 unpaired electrons in the remaining 3D orbitals. Okay, and that's also what we would experimentally find. Okay, that the experimental measurement would argue that there are 3 unpaired electrons, and that's exactly also what valence bond theory would predict. So we can say that the theory is in good agreement with experimental observation, and our theory works well for this case. Okay, then let us go to another example. So this is a tetrahydroxyl zincate complex. So in this case, we have 4 hydroxyl ligands surrounding a zinc 2+. Okay, so again, there would be a dative bond between the hydroxide ions, which would act as the donor, and the zinc ions that would act as the acceptor. So now we would have the task to explain 4 bonds in a tetrahedral shape. So let's see if valence bond theory is able to do that. Okay, so now what is the electron configuration of zinc? So if you have a neutral zinc atom, then you have 12 valence electrons because zinc is in group 12. So that means that the d orbitals are completely full, but also the 4s orbitals are completely full. So now you have a zinc 2+, and that means that you have to remove the 4s orbitals, and that still leaves you the d orbitals full with electrons. Okay, so now in addition to the 4s, you can again assume the 4p orbitals to be valence orbitals. And now you can see if we have actually enough empty orbitals available in order to explain our 4 dative bonds. And the answer is yes, we do. The 4s is empty and the 3, 4p are empty. But again, we have difficulties to explain the tetrahedral shape due to the different shape and the orientation of the orbitals. So now again, what valence bond theory can do is to hybridize these orbitals, mathematically mix these orbitals. And in this case, one would mix 1s and 3p orbitals. So that's a hybridization you know very well from organic chemistry. That gives so-called sp3 hybridized orbitals. And you know that they point toward the vertices of a tetrahedron and therefore is able to explain a tetrahedral shape. So now what we can do is we take our zinc 2 plus with the 4 sp3 hybridized orbitals and take our 4 hydroxyl ligands and orient them so that we can produce orbital overlap between the electron lone pair at the hydroxide ion and the empty sp3 hybridized orbitals at the zinc. So we can produce the overlap, and that would effectively donate the electron pairs at the hydroxide ion into the zinc orbitals and fill them. So now we can again ask, well, what magnetism would we expect? Yes.
Well, it's entirely diamagnetic. It's entirely diamagnetic.
Yeah, that's what we would expect. We'd expect that the complex is diamagnetic, and that's also what we experimentally observe. So that means again that valence bond theory is able to explain the magnetism of the compound as well. Okay, now let's go to one more example. Let's look at a square planar complex such as the tetracyanonickelate 2-. All right, so again we assume that we have 4 dative bonds, and that means that we have a nickel 2 plus, which gets coordinated by 4 cyano ligands. So we have to look at the electron configuration of the nickel next. Okay, so in the neutral state, the nickel has 10 electrons. It's a group 10 metal. So if we go from nickel to nickel 2 plus, we have to remove the 4s. Okay, that leaves our 8 d electrons. Therefore, the nickel 2 plus is a d8 ion. And we can now see which valence orbitals are actually available to make the bonding. So these again have to be empty orbitals. So we see that we have the 4s, the 4p orbitals available to make bonds. So now we have to make 4 bonds. We have 4 orbitals available. So that would be okay. But we also have to explain the square planar shape. So now we could again hybridize. But you know, when you hybridize an s into 3p orbitals, it gives you hybridized orbitals that can explain the tetrahedral shape, but not the square planar shape. So therefore, this is in this case not the route to go. And you see that here, valence bond theory for the first time runs into difficulties to explain a shape. So now, in this case, valence bond theory argues that, well, we can make room in one of the d orbitals by pairing the spins in the d orbitals. So what we can do is, we reverse the spin, move one electron from one orbital into another. So now we have an additional empty valence orbital available, this d orbital. And if we choose this d orbital to be the dx square minus y square orbital, which actually we know lies in the xy plane and points with its lobes into the corners of the square, and mix that orbital with one s and two p orbitals, namely the px and the py, then we arrive at hybridized orbitals, exactly 4 of them, which now point toward the corners of the square, and thereby being able to explain the square planar shape. Okay, so now if you make this additional assumption, then we can take our emitter with its now dsp2 hybridized orbitals, take our ligands, orient the ligands so that we can make dative bonds, approach the ligands correctly, and then the ligands donate the electrons into the metal hybridized orbitals. And we are now being able to explain the square planar shape. Okay? So now we have to give this a critical review, though, because we have made an additional assumption, which is the spin reversal and the movement of one electron into another orbital. And when you critically review this, then there's actually a strong argument against this assumption, which is that spin reversal is quantum mechanically forbidden. So it's actually in this case questionable to make this assumption. Okay, and for that reason, we can say that valence bond theory here actually has some difficulties to explain the square planar shape. We have to make an additional assumption which is not that well justified. Okay, so now we can look at a few other examples. So, for instance, we can look at octahedral D5 complexes. And it's experimentally known that these complexes can either be so-called low-spin complexes or high-spin complexes. And these low-spin complexes, the number of unpaired electrons is being minimized. Okay? And in the respective high-spin complexes, the number of unpaired electrons is being maximized. So if I take out my electron configuration D5, okay, then my high-spin complex would have 5 unpaired electrons, because I can fill all five d electrons, spin up into my 5 different d orbitals. So now if I want to get a low spin complex, then I have to pair them as good as I can. And well, that would eventually mean that we pair these two here with these two, and that would give 1 unpaired electron left. So a low spin complex would have 1 unpaired electrons. So you can again experimentally prove by susceptibility measurement how many unpaired electrons are in the respective complexes. But now the task is, well, can the valence bond theory explain this phenomenon that some complexes make low spin complexes and some make high spin complexes? So again, in this case, the valence bond theory has difficulties to do so. So first of all, we realize that in order to explain octahedral shape, we'd actually have to have 6 empty valence orbitals available. But when you look at how many you have, then that's actually just 4. Yeah. So now you can say again, well, what I can do is I reverse the spins. and start pairing. Okay, and that gives me 2 additional empty orbitals. But again, I have to reverse the spin, which is quantum mechanics forbidden, so it's not actually a convincing assumption to make. But if I do so, then I have the orbitals available that I need for D2 sp3 hybridization. And I can then again approach my ligands and fill my D sp3 hybridized orbitals with electrons coming from the 6 ligands that donate overall 12 electrons. Okay? So this is how I can explain a low spin complex. But now, how do I explain a high spin complex where I have to have 5 unpaired electrons in the final complex? So now you see the previous method does not work anymore, because if I again pair the spins here, I arrive at a low spin complex. So no, there's no way that I can produce my empty d orbitals that I need for the hybridization by spin reversal. And from there you can see that Valence bond theory now runs an additional difficulty. The spin reversal method doesn't work anymore. So what in this case, what Valence bond theory assumes in this case is that I have a so-called outer orbital complex. So this here is called an inner orbital complex, because only inner d orbitals are being involved. But in this case, Valence bond theory assumes, well, in addition to the 4p, we also have the 4d orbitals available. We consider the 4d orbitals as valence orbitals as well. Now, again, you can critically review this assumption. And when you look at the energy of 4d orbitals relative for the 4s and the 4p orbitals, then you realize that they are actually significantly higher. So for that reason, this assumption is again questionable. Why would orbitals having a significantly higher energy still be considered valence orbitals? Why would they get involved in the bonding? There's no good justification for that. But if I just make that additional assumption, then I again have enough empty orbitals available. I can take a 4s, a 4p, and 3 4d orbitals. I can hybridize them, and then I have the correct hybridized orbitals available to explain my 6 bonds in the octahedral shape. Okay, so one more example. Also, the D7 electron configuration knows high low spin complexes. So now, in the case of D7, high spin would mean that I have 3 unpaired electrons, okay, because I must pair the electrons in the first 2d orbitals. There's just no other way, okay. But if I want to make a low spin complex, then I could reverse the spin of 1 electron and fill it with a different orbital, and that would give me only 1 electron left. So a low spin complex would have only 1 unpaired electron. Experimentally, I would be able to measure that some complexes have 3 unpaired electrons and some other complexes have just 1. So now again, would valence bond theory be able to explain that? Well, so again, we have to explain octahedral shape. So to begin with, we see that, well, we have 4 empty orbitals available. That's the 4s and the 4p. Now, in this case, could we create additional orbitals, additional empty orbitals by spin reversal? So now you see that, well, you can reverse the spin of 1 electron and fill it into this orbital, But with the second electron, you can't do this anymore because there's just no additional spin pairing possibility. So what valence orbital does in this case is, well, it says we do reverse one spin, but we assume again that the 4d orbitals are being moved, and we can just move one of our 3d electrons into a 4d orbital. So now we have 2 3d, 4s, and 3 4p orbitals available for bonding. We can hybridize these and then create our donor accept interactions and fill these D2 sp3 hybridized orbitals with electrons, making our 6 bonds. And this one electron here would be a 4d orbital, and that would be the one unpaired electron that we would experimentally measure in a low spin complex. Yeah. So now again we see that this is not making a whole lot of sense, because why the heck would this 3d electron want to go into this energetically much higher 4d orbital? So we basically just do what we need to do in order to explain the number of bonds and also the shape, but the assumptions that we have to make to do so are not well justified. So similar difficulties arise when we want to explain an octahedral D7 high spin complex. In this case, we can assume a so-called outer orbital complex. So again, we assume that we have the 4d orbitals involved. We do not reverse any spins because we have to explain 3 unpaired electrons. So therefore, we hybridize 2 of the 4d orbitals, 4s and 3 4p's. Okay, so that gives us again the dsp2 hybridized orbitals that we need. So again, we can make our donor acceptor interactions and fill the electrons into the D2 sp3 hybridized orbitals, making our 6 bonds, explain the octahedral shape. Okay, so what you see from that is that valence bond theory can do something in order to explain coordination compounds, but overall it doesn't do very well. So it does very well in organic chemistry, in main chemistry, but for transition metal complexes, it has significant limitations. And therefore, valence bond theory has only relatively limited use in coordination chemistry. But nonetheless, it has some, and therefore I wanted to explain the principles. Okay, we have still a few minutes time, so we can maybe start with the next bonding theory, which is the crystal field theory. Now, I said previously that the crystal field theory is based on repulsive electrostatic interactions. So in this case, we assume that well, the electrons in the transition metal and the electrons in the ligand, they repel each other, and that influences the energy of the orbitals, and the respective energy changes that occur can then explain very well the shape and the magnetism and also optical properties of the coordination compound. So let's see how this works exactly. So let us start out with a very generic case. Okay, let's assume a metal ion which is surrounded by a so-called spherical crystal field. The spherical crystal field is hypothetical. It assumes that basically you have a uniform spherical electron density around your transition metal. Okay, so now there will be isotropic electrostatic repulsion between the electrons in our electric field and the electrons of our transition metal. Okay, so therefore, what will happen to the transition metal d orbitals? Well, because of the repulsion, the energy will go up. And the energy will go up by exactly the same amount of energy, just because the crystal field is spherically and completely isotropic. Okay, so now let's go from this hypothetical case to a practical case, and do not assume a spherical crystal field, but an octahedral crystal field, in which ligands containing electrons surround the transition metal octahedrali. Okay, so now our crystal field is not completely isotropic anymore. So we have actually more electron density on the axes where the coordinates are in comparison to locations in between the axes. Yeah. So where the z-axis would be occupied by these two ligands here, the x-axis by these two, and the y-axis by these two, if we define the axes this way. Yeah. And now you know that the d orbitals of a transition metal have a certain orientation. Yeah. So the dz square orbital is oriented along the z-axis. The dx square minus y square orbital has lobes on the x and the y-axis. Okay. For that reason, there is strong electrostatic repulsion between these two orbitals and the octahedral crystal field. And therefore, relative to a spherical crystal field, the energy of these two orbitals is higher. So now, vice versa. So these orbitals here are also called Eg orbitals. That is because the dz square and the dx minus y square have Eg symmetry in the octahedral point group OH. Okay, so they are symmetrically degenerate. Okay, and remember when we discussed molecular orbital theory, we said that when two orbitals are symmetrically degenerate, they're also energetically degenerate. And this explains why they both have the same energy. Okay, so they have very different shapes, and one would at first glance think, well, the electrostatic repulsion between these two orbitals and the octahedral crystal field may not be equally large. Yeah, but it is actually equally large, and you can make the symmetry argument to explain this. So now, vice versa, we have the remaining orbitals, and we see that the lobes of these orbitals are in between the axes. So therefore, electrons in these orbitals experience relatively small electrostatic repulsions coming from the ligand electrons. And for that reason, these orbitals have a lower energy relative to the spherical case. Okay? Note though that in comparison to the case where you have no crystal field at all, of course, all orbitals are elevated in energy, but not equally so. So the Eg orbitals have a lower energy than the other three, which are, by the way, called T2G orbitals, because they have T2G symmetry in the octahedral point group, OH. Okay, so now the energy difference between the T2G orbitals and the Eg orbital is called delta O. And for statistical reason, or no, not for statistical reasons, but for energy conservation reasons, the energy of the Eg orbitals is elevated by 3/5 of delta O relative to the spherical case, and the energy of the T2G orbitals is decreased by 2/5 delta O relative to the spherical case. Okay, then I see our time is over, and we will apply crystal field theory to the other shapes as well, and then see how well crystal field theory works in order to explain experimental phenomena. So let's stop at this point.